All right, so we're going to come up with the formulas for double angle identities. Double angle identities are identities where your angle is doubled or multiplied by 2. So we can use the sum identities that we already know to figure out the formula for the double angle identity. So sine of 2x I can rewrite as sine of x plus x. And then I can use my sum identity for the sine using this first angle is my x and the A, and my second angle is my b. My sine identity is sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle.
Tyler Kite, please report to the library. Tyler Kite, please report to the library.
So anyway, when you add sine x, cosine x together with sine x cosine x, we get 2 sine x cosine x's. So that's my double angle identity for sine. So what it's going to allow us to do is when you have an angle that's 2x, you can rewrite that so now that your angle has just a coefficient of 1. So it can help make your angles match with other parts of the problem there. So we'll come up with the identity then for cosine of 2x, much the same way there. So cosine of 2x, I can make that x plus x. So it's cosine, think of these as a plus b. It's going to be cosine of my first angle times cosine of my second angle. Remember, the symbol in between for the cosine is the opposite, so instead of plus, this will be minus sine of the first angle times sine of the second angle. So cosine of 2x would be cosine squared minus sine squared. Now, we're going to come back to this one in a second here because there's a couple other ways that we can write that same identity. And then finally, we'll do the tangent for 2x, much the same way. So tangent of 2x, we can rewrite that as tangent of x plus x. So that would be tangent of my first angle plus tangent of my second angle divided by 1 minus tangent of my first angle times tangent of my second angle. So tangent of 2x, I would have 2 tangent x's in the top, and I have 1 minus a tangent squared x in the bottom. So those are your 3 double angle identities that you need to know. And they're in the box. Your box, I think, is green in your booklet there. So if you look at cosine 2x, there's 2 other identities written below here. And we didn't talk about those. If you look back at your cosine identity, so cosine of 2x, we developed and we said it was equal to cosine squared minus sine squared. These other 2 versions of that identity, you can use if you have an equation problem, you only want cosines in the problem, you only want sines in the problem. So maybe you want to take out this cosine squared and make it 1 minus sine squared minus the sine squared that's already there, and you have 1 minus 2 sine squared. So that's where this second identity then is coming from. And same thing with that next one, the 2 cosine squared minus 1. We would do the same thing here. Instead of taking out the cosine squared, we'll take out the sine squared. So sine squared is 1 minus cosine squared. So you have cosine squared minus 1 minus a negative would be a plus cosine squared, which gives us 2 cosine squareds. Right, so that's where that third identity then comes from there. If you know this first one, though, you can always come up with those other 2 by just replacing, just like we did there. All right, so let's try a few of these problems then. So for this one, you have sine of theta is 12 over 13, and theta falls between pi over 2 and pi, which is just a fancy way of saying the second quadrant. So we'll draw that triangle. It's sine of theta, so it's 12 over 13. Opposite over hypotenuse, there's my theta. And that third side then would have to be -5 using the Pythagorean theorem. Now they want to know what's the sine of 2 theta. You can't just double the lengths of the sides there. You have to actually develop the formula. So sine of 2 theta, I have to expand that using that double angle identity is equivalent to 2 sine of theta cosine of theta. Now I know about theta, I don't know about 2 theta, but once I expand that, I can use that reference triangle that I just drew. Sine for angle theta is 12 over 13, opposite over hypotenuse. The cosine for angle theta would be adjacent over hypotenuse, which is negative 5 over 13. And then multiply in fractions, you can make that 2 over 1 if you like. Top times top times top will give me what? Negative 120. And bottom times bottom times bottom is 169. And then I could solve cosecant of 2 theta. We didn't do any double angle identities for cosecant or secant or cotangent. But if I know that the sine of 2 theta is equal to negative 120 over 169, cosecant is 1 over the sine of 2 theta, which is just the reciprocal of that fraction that we have there. So 169 over that 120, and then you put your negative wherever you like, out in front of the fraction, top, bottom, it doesn't matter there. So all of these reciprocal identities will just flip the fraction then. So cosine of 2 theta, you can pick which of the identities you want to use. It's actually easiest if you use cosine squared minus sine squared, because then you won't have to simplify as many pieces to this. So cosine 2 theta is equal to cosine squared minus sine squared. So cosine squared from that triangle there would be negative 5 over 13. And that fraction is squared. And then sine is 12 over 13. And that fraction is squared. So that's 25 over 169 minus 144 over 169. And if I combine that, I get negative 119 over 169. And then I can do the same thing for the secant. That's 1 divided by the cosine. So it's just the reciprocal of this fraction here. So it would equal 169 over negative 119. And again, you put that negative in the top or the bottom there. All right, and then finally for tangent 2 theta, we could, if we wanted to, just make the sine of 2 theta divided by cosine of 2 theta, because I already found those two values instead of using the tangent formula. Sine of 2 theta, that was negative 120 divided by 169. Cosine was negative 119 divided by 169. And I can just change that to multiply by the reciprocal. And that'll give me positive 120 over positive 119 for the tangent. And again, if I know the tangent, then the cotangent's just the reciprocal of that. So this is going to be cotangent of 2 theta would be positive 119 over positive 120. All right, and then let's look at a couple of the homework examples that follow the same problem here. So they gave you this triangle, they gave you angle theta and the two sides 3 and 4. That hypotenuse, I put it in green, you had to come up with that, which is 5. So for the first problem, then they want to know what sine of theta is. Well, our angle in the problem in that triangle there is just theta. So we already know that value. So the sine for that triangle then is 3 over 5. For number 3, they want to know what cosine of 2 theta is. So for this one, we don't know 2 theta. And again, we can't just double the sides. So you have to expand this using your identity. And you can pick one of the 3. I'm going to stick with cosine squared minus sine squared. My cosine for that triangle, because my angle is now theta, is 4 over 5. My sine is 3 over 5, and that's squared. So 16 25ths minus 9 25ths. 16 minus 9 is going to give me 7 over 25. All right, and then number 5, they asked for tangent of 2 theta. Now, if I had to find sine of 2 theta, I could just do the same thing I did with the notes there and do sine divided by cosine, but I didn't find sine for this one, so I'll use the identity. The identity for sine 2 theta is 2 tangent theta would be 2 tangent theta over over 1 minus tangent squared theta. So looking at that triangle, my tangent is 3 over 4. 1 minus 3 over 4 squared. So I'm going to reduce this numerator here. I would have 3 halves in the top. I have 1 minus square root of the top is 9, square root of the bottom is 16. So I have 3 halves in the top. This would be 16 over 16 minus 9 over 16 would give me 7 over 16. And then I can multiply by the reciprocal. And these guys would reduce. So I'll have 24 in the top, and I'll have 7 in the bottom for that one. So 24 over 7. And then finally, cosecant of 2 theta. If I had to find sine, I would just take the reciprocal. I didn't find sine for this one. So cosecant's 1 over sine 2 theta. And sine 2 theta is 2 times sine theta cosine theta. So I'll just simplify this fraction. Sine for theta is 3 over 5. Cosine for theta is 4 over 5. If I multiply this fraction, I still have 1 in the top. I'm going to have, 6 times 4, so that's 24. Bottom times bottom times bottom will give me 25. And 1 over 24 fifths is just 25 24ths. All right, and then 19 followed this problem. This was similar to what we did in class 2. So they said u falls between pi and 3 pi over 2, so that triangle will be in the 3rd quadrant. And they said that tangent of u is 1/2. So in the 3rd quadrant, tangent is positive. Opposite side would have to be -1. Adjacent side would have to be -2 in order for that to work. So Pythagorean theorem will give you square root of 5 for that hypotenuse. Sine for 2u then, expand it using your identity. It would be 2 sine of u, cosine of u. Using that triangle, since I know about angle u, my sine would be -1 over root 5. And the cosine for that triangle is -2 over root 5. All right, multiplying numerators together, I'll get +4. Multiplying denominators together, I get +5. Using that same triangle, cosine of 2u is cosine squared u minus sine squared u. So in that triangle, the cosine is -2 over root 5, and it's squared. The sine is -1 over root 5, and it's squared, so I have 4/5 minus 1/5 gives me 3/5. And since they wanted tangent for this one, and I've already found sine and cosine, I'm just going to make this sine of 2u divided by cosine of 2u. So sine was 4/5, cosine was 3/5. If I simplify this, I get 4 over